Alright, hello everyone. Welcome back to some more data analysis. Today we are going to be discussing the LASSO, and so I'll just kick it right on off. For references, this subject is not found in the Truth About Linear Regression, so if you're looking for additional reading, you'll have to look into Intro to Statistical Learning. Okay, so in the previous lecture on model selection, we talked about this idea that we could penalize the least squares estimator in a way that this penalty would induce variable selection, and this is that concept. So this is the lasso. But before we get to actually introducing it, what that penalty looks like on the mean squared error, let's introduce some notation. And so in the past, we've used this norm. Particularly in the context of ridge regression, we use this norm to indicate the length of a vector. And remember, just the length of a vector is the square root of the sum of its squared entries. Okay. Another notion of length for a vector is by summing the absolute values of its entries. So this is denoted by it's called the one norm. Okay. And we denote the one norm of a vector as the sum of the absolute value of its entries. Okay, so this norm here is our sort of typical norm. It's sometimes called the Euclidean norm, sometimes called the 2 norm, and this is called the 1 norm, where we sum up the absolute values of the entries of a vector. So this 1 versus 2 language, the 2 norm versus the 1 norm language, it comes because if you use p equals 1 or p equals 2 in the following expression here, for p equals 1, you get the sum of the absolute values of the entries. For p equals 2, you get the sum of the squares of the entries, and you take the square root. So this is where the origin of 1 versus 2 norms come from. So using 1s and 2 norms, the ridge estimator is you minimize the mean squared error, and then you add some squared 2 norm penalties. So this is the squared length of b, where it's assessed using sort of the usual norm, okay? The usual Euclidean, i.e. the 2 norm that we saw. And just to introduce a little bit of extra confusion, but I mentioned this before, I've written this here without the penalty being lambda over n, just wrapping the n into the lambda. So I mentioned this when I introduced ridge regression, but this is another way to write it. Okay. So the lasso is you minimize the following. So you minimize in this vector b, you have a mean squared error term. This is as expected. Again, y as a vector of observations of y, x is a design matrix, and then what you do is, instead of adding a squared 2 norm to the end as in ridge regression, you add the 1 norm. Okay, so we have a 1 norm penalty here. Okay, so similar to ridge regression, it's typical that the intercept is not penalized here. So you can write this as summing the absolute values of the non-intercept entries, the same way that in the ridge regression you can sum the absolute values of the you can sum the squares of the values of the non-intercept terms. Okay. So we can write this in scalar notation if we want. This is minimized over vectors b, the mean squared error here, plus lambda times the 1 norm penalty, the sum of the absolute values here. And here I've gone from I equals 1 to p to emphasize in this expression I have not penalized the intercept. Okay. What is LASSO? LASSO is an acronym. It stands for Least Absolute Shrinkage Selection Operator. It's a mouthful. You can use LASSO without remembering this, and I think it's one of these acronyms where the acronym probably came before what it means, right? But we'll actually explain what it does mean. So this least absolute shrinkage selection operator. So Least absolute, this is the one norm. We're adding this absolute value penalty. Okay. Shrinkage. So this is called a shrinkage method. Ridge regression is also called a shrinkage method, but the reason is that well, let me jump back to the optimization problem. So we minimize mean squared error plus some one norm penalty here. And so what's happening is by penalizing this the length of b here, we are encouraging it to be small, right? So this is why this is a shrinkage, called a shrinkage estimator, is because we're penalizing, thereby encouraging the result to have small length. Okay. The selection, so that's least absolute shrinkage. The selection part in the LASSO acronym, well, this refers to the LASSO's ability to do the variable selection, and we'll talk about this in a little more detail through some examples. But indeed, LASSO can do variable selection. When you add this penalty, you get you have the ability to do model selection. And then lastly, the operator. I think this is just something that was tacked onto the end because they like LASSO as a word better than LASS. But anyway, so least absolute shrinkage and selection. And so you can use the LASSO estimator when you have too many predictors and you want to find which ones are relevant. Okay, this is similar to our previous lecture on variable selection. Another way to say this when you have this too many predictors and you want to decide which ones you should include is that you would like to estimate a sparse beta. Okay, and a sparse beta is one with many zeros. So if your true beta, you have many predictors and you're trying to estimate a beta, and many of them are 0, that is, many of the predictors are irrelevant and only some of them are, this beta is said to be sparse. Okay, so it has many zeros. Sparsity is a very big deal. You can imagine sort of any time you have a situation where you have too much information, only a subset of which actually matters, there's a sparsity assumption in there, and in particular from a tractability perspective, a lot of times a sparsity assumption makes intractable problems more tractable. You can do things like sparse linear algebra when your matrices or your vectors have many zeros, and see speedups in these kind of operations and storage requirements and things like this. So this is just a small taste of the world of sparsity. It's a big deal, but in LASSO, we are trying to estimate a sparse beta, i.e. one that has many zeros. Okay. So we place special emphasis when we're doing sparse estimation. If we're able to come up with an estimate which is 0, we can remove those predictors from our model, right? So near 0 is okay, but if we could actually set some of these equal to 0 in our estimate, that's even better for us because then we can completely remove those predictors, right? So the problem is the same, of course. This idea that we have many predictors, some of which matter, some of which don't. It's the same problem that we are addressing using the subset selection and stepwise regression. So yeah, same idea, but the LASSO, we emphasize this notion of sparsity because we do feed all of the predictor information into our model and we let it decide, as opposed to sort of the greedy selection process, which is separate in the sense that we are grabbing a predictor and then building a model, and then grabbing another set of predictors and then building another model and comparing them. Whereas this one, we can just throw all the predictors into the estimator and let the estimator find a sparse solution. Okay, it is a fact that the LASSO estimator tends to be sparse, so it tends to have many zeros. It's not clear from looking at this expression why that would be, but there's some intuition behind why that is. And so let's talk about that now. So why is the LASSO solution sparse? If I solve this problem, I take my mean squared error and I add a one norm penalty on it, why will the solutions be, the beta hats that come out of this LASSO estimator tend to have many zeros? Okay. So we're going to consider just a two predictor setting. Okay, so two predictor regression through the origin example. This is just for simplicity because the intuition will carry over. So we have n observations and two predictors, and of course the LASSO estimator is we are minimizing mean squared error. So here this B is in R2, right? We're only estimating two values here, and regression through the origin means that we're two predictors, two values. We don't have a third value for an intercept, so we have a mean squared error plus, and here I've just written out the one norm, the sum of the absolute values of the entries of the B vector. Okay, so in your vector calculus class, you saw, or I hope you saw, the theory of Lagrange multipliers. And without going into the weeds of Lagrange multipliers allow you to write penalized problems as constrained problems and vice versa. So it allows a translation between you have a penalized problem and a constrained problem. And loosely what happens is you put the constraint up into the objective with a suitable penalty. So by using Lagrange multipliers, we can show that this is a constrained problem where we have minimized mean squared error subject to an L1 norm penalty. Then we have an equivalent version where this is a gamma here, this is a lambda here. So these lambdas and the gammas, they're not necessarily the same, but the theory says for some gamma there exists a lambda such that this problem is equivalent to this problem. So what I'm going to do here is use this theory to write the LASSO problem as an equivalent constrained version. And in practice, this is not how we're going to do it. We're going to solve the above version, but by writing it as a constrained version, we're going to be able to see some more intuition for why the solution should be sparse. It's easier to see in this version. So, of course, this constraint here down at the bottom, this is a box. If you write out what this inequality is, you will be able to see that it looks like this. Okay, again, we're working in two dimensions here, and so the inequality is the inside of this box. Okay, and for simplicity, again, because we're just thinking about why these solutions should be sparse, we're just trying to build intuition here. We're going to assume that gamma is 1. Okay, this just makes our life a little easier. Then we know that the vertices here should be, this is 1, 0, 0, 1, so on and so forth. Okay, so let's draw out a picture of this optimization problem. Minimize mean squared error subject to one norm constraint. So here's what I have. So this is for some sample. I have the one norm box. Okay, notice the one norm box has its vertices at 1, 0, 0, 1, negative 1, 0, and so on, right? So this is the one norm box that we just drew. And this is the least squares estimator. Okay, so the least squares estimator is the solution to the problem of minimizing mean squared error. Okay, this is just for some x's and y's that I generated, but this is the least squares estimator. And if we didn't have the penalty, right, the solution, of course, to our minimizing the mean squared error problem would be this least squares estimator. But as it is, we have this minimized mean squared error subject to this box constraint. So everything else without this box constraint, this would be our solution, but we have to have our solution be inside of this box. Okay. So what I'm going to do is I'm actually going to draw level curves of the mean squared error function. So what I mean by that is I can think about this mean squared error, right? It has its minimum at the least squares estimator. But if I were going to add a little bit and say, okay, I'm permitting this mean squared error to go a little bit above the value it takes with the least squares estimator, right? Then I can draw a curve, which is what are all the values what are all the b values which allow this mean squared error to take the value which is slightly above the value taken for the least squares estimator. So if I draw some level curves, okay, so I see that the minimum mean squared error is 2.23. Okay, and then this circle here is a plot of all of the b values where the mean squared error is 3.41. Okay, and so on and so forth. So I can increase these circles, and when I increase these circles, this represents sort of increasing my mean squared error, right? So I'm increasing my mean squared error as these circles get larger, and I can see how I'm increasing it, to what value. Okay, and notice these level curves, where they first intersect the box, right? So what's happening is I'm increasing my mean squared error. I'm like, okay, I really need to be in the box for this optimization problem to be solved because this is constrained. And I hit this corner of the box. And when I hit this corner of the box, this is the minimum mean squared error. So I'm slowly increasing the mean squared error as I'm drawing these ellipses. At this point, I have the minimum mean squared error. It's 12.115. Okay, and I'm also in the box. So as I'm increasing further than this, obviously my mean squared error is larger than I would like it to be. Of course, I'm in the box, so the constraint is satisfied. But this is the solution to my lasso problem, because I've increased the mean squared error, a minimum amount, such that I'm in the box. Okay. But then notice this solution here. It is on the vertex of the box, right? Because this is on the vertex of the box, this lasso solution has b1 equal to 1, right? And b2 equal to 0. So this solution has b2 equal to 0, right? So my least squares estimator didn't have b2 equal to 0, but as I was compromising mean squared error between this constraint of ending up in the box, I have hit this point, which was a vertex of the box, and the vertex of the box, these points tend to be sparse. They have b1 is 1, b2 is 0. Okay, so in general, this is the intuition actually, and this is sort of very popular intuition. There's a number of textbooks which have this or a similar graphic on it. This idea that I take my, you can imagine a different least squares estimator. I take my least squares estimator, and I blow up the mean squared error until I first hit the box, right? And what will happen is that it will tend to, these ellipses, as they grow large, they will tend to hit vertices of the box. It is possible, if you were to have some least squared error, which is here, and some level curve which look like that, it's possible to have a solution which is not sparse. But it is more common that you will intersect the box at a corner, and when you do, this represents a sparse solution. Okay, so this is sort of the geometry of the situation. The level curves tend to intersect the corners of the box, and when you intersect the corners of the box, you end up with sparsity, and this is why the lasso solution, the lasso estimator, is sparse. Okay, so so that is why the lasso is sparse. How do we actually find the lasso? We have this minimization problem with this L1 norm at the end of it. It's not differentiable because this is the sum of absolute values at the end here. The absolute value function, of course, is not differentiable. So we can't take a derivative and set it equal to 0. We have seen a previous estimator which is not differentiable. This was the least absolute deviation penalty, or at least the LAD estimator, the least absolute deviation estimator. And the trick that we used to overcome that was to use linear programming. But we can't use linear programming here because we have a quadratic term in B and then the sum of absolute values here. So if we just had the sum of absolute values, we could use a linear programming trick. So we can't use a linear programming trick. Punchline is the tools that we have so far don't work for this problem. Optimizing this expression is an interesting problem, but you will see some tools for doing it in your nonlinear programming course, which is upcoming. But the point is, R can do it for us. We will allow R to do it for us. The optimization, we won't spend too much time talking about it, except that it falls outside of the functions that we have minimized so far. That is, we can't use the linear programming trick, and we can't just differentiate and set equal to 0 using our matrix calculus skills. One result of the fact that this is non-differentiable is that properties, things like variance, hypothesis testing, so on, they're harder to derive for the lasso than even in the rigid case. So that's just something to note that falls out of this optimization problem. We do know that the lasso estimator is biased. Okay, similar to the ridge estimator, when you put this penalty on, you induce some bias, right? I have this comment here, see previous graphic, right? So if we see the previous graphic, well, what's happening is we're taking this least squares estimator and we're pulling it to be something else. So you can imagine that if this least squares estimator tends to, is unbiased, right, as the least squares estimator is, then what the lasso estimator is pulling it away from what it would usually tend to be, and this is inducing some bias. Okay, so in R, we compute the lasso using the GLMNet or the caret interface to GLMNet. So this is exactly the interface we've used with the ridge estimator, but here we set alpha equal to 1. Remember, alpha was another penalty parameter, which I said we're going to talk about later when we introduce ridge regression. Now we're talking about it. Alpha equals 0 means, if you remember right, is the ridge estimator. And alpha equals 1 is the lasso. Okay, so this alpha allows you to choose between the two of them. If you choose alpha between 0 and 1, you get a compromise between the ridge and lasso. And so what you have is a minimization problem where you minimize mean squared error, and then you add a weighted penalty. So here's a lambda, and then what you do is this alpha allows you to choose the weight between a squared 2 norm, that is, this is a ridge penalty, and a lasso penalty. So you see, if alpha is 0, what happens is, well, you get no lasso penalty, you only have ridge. If alpha is 1, you get no ridge, you only have lasso. Okay, so this alpha is a parameter which allows you to compromise between these two penalties here. And this penalty, where you allow an arbitrary alpha, is called the elastic net. This elastic net penalty is what gives GLM net. So this is generalized linear model net. The net in elastic net comes from this general formulation that the package allows you to solve problems of this form. Okay. The benefit of using an elastic net penalty is that you can address multicollinearity concerns and sparsity concerns simultaneously. Okay. And so, yeah, this is the elastic net, and now we have the full suite of tools available to us from the GLMNet package. Okay, so let me jump into R. What we're going to do next is an example. Some homeworks ago, after we introduced categorical predictors, we used this birth weight data set where we were predicting the birth weight of babies using attributes of their mothers. We're going to do an example using the lasso estimator on this birth weight data set. So let's switch over to R. Okay, so as usual, I will post this code on the course website, but what I have here at the top, this is just for people who are interested, is the code. I'm just going to run quickly through it to generate the plots that we saw in the lectures. So that is this plot where we had the least squares estimator and the level curves and things like this. So if you want to see how I made that, you can refer to this code. And okay, so then let's go into we'll jump into the birth weight example. We're going to do elastic net and lasso. If I can just zoom in here. So I'm going to load the mass library. That's where the birth weight data set comes from. I'm going to set my seed. If I set my seed, then my cross-validation will be able to be rerun, and I'll see the same results. I'm going to load up the birth weight data. Just a quick reminder, this birth weight data is 189 rows, 10 columns, and it's collected at a certain hospital in Massachusetts in 1986. And we want to predict babies' birth weights using all these attributes of their mother's age, whether or not mother is a smoker, the number of previous preterm labors, so on and so forth. Okay, and remember that we had all of these categorical variables, and most of them were coded zeros and ones by default. The only one which was not, which was problematic, was this this race category. And so I'm going to make sure that R treats these races as categories by just reminding R that this race variable should be a factor. Okay. I can leave the zeros and ones for binary variables like smoking. 0 for non-smoker, 1 for smoker. I can just leave them as binary variables. And then in the homework assignment from some time ago, we discussed different ways to break numeric variables into categories. One example we looked at was the number of previous preterm labors. I'm just going to leave these numeric variables as numeric variables and not break them into categories, even though we saw in the homework that sometimes it is good to do so. Okay, so I'm going to load up GLMNet. I'm going to use the GLMNet the GLMNet directly instead of caret, just as as a first pass. So I'm going to feed. So the cv.glmnet is the glmnet function that does cross validation. I'm going to set as my x. I'm going to feed it a design matrix here. So here cv.glmnet wants a design matrix and a response vector. So I'm going to feed it this design matrix, which is predicting birth weight as a function of, and here I have all interactions. Okay, so this is all factor crossings when I write this square here. Everything except low birth weight was a category indicating low birth weight, so I don't want to use it as a predictor. When I do this square here, according to R's syntax, I get all factor crossings between these variables. I'm not going to add an intercept, and the reason is that I'm going to use GLMNet's tools to add in the intercept. So I'm not going to add the intercept into the design matrix. Instead, I'm going to use intercept equals true. And so this will add the intercept in a way that it's not penalized. And the benefit of that is that it doesn't do model selection for the intercept term. It does model selection for all the other predictors. So let's run this. And then let's look at the coefficients. Okay. So what's happened is I'm looking at the coefficients here, so there's quite a few of them, but this dot here, so let me back up just a moment. What's being returned is a sparse matrix, and this dot here means that the entry is 0. So all the dots represent zeros, so my returned model has an intercept term. It has the mother's weight, the mother's race. It has an interaction between age and race. It has an interaction between age and smoking. So these interaction terms are selected, but many of the interaction terms are not selected, right? And so we here have a model where we've maybe reduced all these different interactions terms to, I don't know, maybe 8 terms or something like this. And this demonstrates the output of what you might see in a LASSO problem. You've fed in all the predictors. You've returned a sparse solution, which reduces the amount of predictors in a problem. If I plot the GLMNet, the result of GLMNet, what I see is a plot which indicates the how the mean squared error is decreasing with lambda. So in particular, this is the log of lambda down at the bottom. Okay, so we have a this is a plot, and the mean squared error. So this is the mean of the mean squared error because we're doing cross validation. Okay, and then these brackets here indicate plus or minus 1 standard deviation from that mean. So we see we're decreasing, we're decreasing, we're decreasing. There's a point here where we have minimum mean squared error, okay? And then this second line indicates this is a special cutoff, but this is the most penalization such that our model is within one standard deviation of the smallest. And this is a heuristic that the authors of Intro Statistical Learning like. I think it's intuitive and nice to use, but their heuristic is that you should choose the smallest model such that its mean RMSE, or mean squared error here, is within one standard deviation of the smallest. So their idea is that you should choose a simple model that is close to the best. You should prefer a simple model. You should prefer a model that's good. And the way that they formulate this trade-off is that you should be close to the best in the sense that you're within one standard deviation of the mean squared error of the best, and then choose the simplest model that you can within that region. Okay. So we can use caret to do to construct lassos. In particular here, I'm going to choose alpha to be 1. So this is pure lasso. If in this example here, cv.glmnet fits an elastic net model by default. cv.glmnet model. cv.glmnet fits an elastic net model by default. So this is what I'm getting. But if I use caret, I can just specify my alpha value is 1. And when I specify my alpha value is 1, this means I'm doing strict lasso, no elastic net. Okay, I'm choosing a lambda sequence and then specifying my cross validation. And so when I run this, I get a similar output to caret. So this is printing many outputs. I have my lambda value. I have my RMSE. This is my mean RMSE over the cross validations, right? So I take each one of the folds equal to my testing set and the rest equal to my training set. And so I can see what's happening to my RMSE as lambda is increasing there. Get the coefficients of the model, and again, what I see is I have an intercept term. I have certain predictors being selected, and certain interaction terms being selected by the lasso model. Okay. So yes, and again, a big idea. We have reduced the number of predictors because these lasso solutions tend to be sparse. I can plot. Here I'm going to plot the lasso or the GLMNet output, but instead of just running plot, I'm going to do xvar equals lambda. When I do this, what's happening is I have a plot. This is kind of interesting because it shows what's happening as lambda increases. So as lambda increases, I see each one of these colored lines is a coefficient. So as lambda increases, we see that some of the coefficients are going to 0, right? So when they come in and hit this, so this, I don't know which coefficient this is, but as lambda increases, the coefficient gets smaller and smaller and smaller until it's 0. Okay. And similarly for this black line, we see this what's happening is lambda is increasing. We're encouraging more and more sparsity, right? Until with lambda way over here, we have no solutions which are non-zero, no coefficients which are non-zero, right? And in between, sort of, we have this compromise between the high penalty and choosing a sparse solution. So if I just plot the best lambda found from caret here, and again this is on log scale, so I have to make sure I plot the log here. This point is the value of lambda at which caret has identified us having the lowest cross-validated RMSE. So this value here, we have some coefficients which are non-zero, many of which are 0, and so this sort of represents. This is a nice graphic because it illustrates the decay of the coefficients as you increase the penalty. If I were to increase lambda, I will get a smaller model. Okay, so in the here I'm specifying that lambda should be 200, whereas in the previous example I took lambda between 30 and 70. Here I'm saying lambda is 200, right? If I do this, then I see that well, I have set many coefficients in my model equal to 0. In fact, there's only one coefficient, this UI coefficient, which was not set equal to 0, besides, of course, the intercept. So, yeah, this is just capturing the trade-off between large penalty parameter and having your coefficients, your estimated coefficients, be 0. Okay, and then another thing you can do with LASSO is that you can take the predictors, which are selected to be non-zero from your LASSO, and you can refit using a usual LM. Okay, so the advantage of this is that you're going to let the LASSO do the variable selection for you, but then you'll be able to do things like compute variances and compute confidence intervals and things like this. So what I've done in this last part here is I take the non-zero indices, okay, and I am going to look at what they are. So I say, okay, what coefficients were non-zero in my LASSO estimator? And I say, well, I have the mother's last weight, certain race categories, a certain interaction between ages and race, so on and so forth. And so I'm going to build a linear model which has these predictors. Okay, so I have a factor crossing between the mother's weight, their age, this UI predictor, and so of course this is going to give me the mother's last weight predictor, right? Because this is the factor crossing. And just expanding, what I've done here is I've built a model which includes all of these terms. So I've said, okay, if I need this interaction term, I'm going to include the appropriate factor crossing, and that's this factor crossing. So this model is actually larger than just the coefficients which are non-zero in the LASSO estimator, but I'm doing this to reflect best practice in the sense that I'm including the factor crossings where I have to, right? And so, and for example, if one we see trends in the model with a certain race, I'm going to include all categories of race in the model, again, just to reflect best practice. Okay, and so again, the idea here, this is nice because I can do things like compute confidence intervals if I like, and in this sense what I'm doing is I'm using LASSO just to do variable selection and select which predictors are important to my model, and then I'm using the good theory associated with the usual least squares estimator. Okay? Alright, so let's conclude about LASSO. So we've seen that LASSO can be used for variable selection. We've seen it done in practice. In this R example we were looking at just a moment ago, we've seen it, why it is the solutions tend to be sparse just by looking at some of the geometry. The big distinction between LASSO and the previous penalized estimator we've used, which was ridge regression, is that we changed penalties. So we're using a 1 norm penalty instead of a 2 norm penalty. Okay, we can compromise between these two penalties, 1 norm and 2 norm, using this alpha value that we saw in the elastic net, and of course that gives us the elastic net regularization, where we balance between sparsity concerns with the 1 norm and multicollinearity concerns with the 2 norm. You can use GLMNet, or you can use the caret wrapper for GLMNet to build ridge ridge models, LASSO models, and elastic net models. remember that there's some unattractive theory associated with LASSO in the sense that it does shrink your coefficients, so it does induce bias. Therefore, that's one limitation. Another limitation is that we don't have some of the nice theory like hypothesis tests and confidence intervals and things like this. Things like VIFs, we can't compute in LASSO, which is a drawback, and so one can get around this, as I did in the R code just a moment ago, by using the LASSO for variable selection and then refitting a linear model on the variables that are selected by LASSO. Okay, so that is what I have for you today, and I look forward to seeing everybody next time.